Going live here on YouTube. Even though they banned me a couple of weeks ago, we're back. And with everything that's going on in the world today, as the guy that calls himself the president continually melts down, today we're going to deal with something called antimicrobial resistance, the inability of antibiotics to really do what they need to anymore. And COVID is one of the prime examples of that. We don't have an antiviral. We don't have anything that's really highly effective. You know, we've heard all the things of hydroxychloroquine. Yeah, it's somewhat effective. And most of the other things are somewhat effective. We're even using antiparasitics now. We're using veterinary medicine now. We're struggling to find something that's going to work. So what is it that's making these antibiotics have such a hard time? Is it the antibiotics themselves? Is it the antivirals themselves? Or is it us? Are we changing in some way? Are our bodies doing something differently in the last couple of years? And the answer to that is definitively yes. And I'm going to try to keep this simple and sweet today. This comes out of a university called Exeter, which is I believe, in England. And it says this: decreasing bacterial acidity could help reduce antimicrobial resistance by eliminating bacteria that can survive being treated with antibiotics. So what's that mean? That means as God created our bodies, and this is a beautiful thing. I want you to just pay attention to this. You know, we say that our bodies are 70% fluids, water-based. You know, our bloodstream, our lymph system, our tissues, close to 70%. Now, in order for a bacteria to move or a virus to move within our body, so let's just use the example of COVID coming in through our lungs primarily. After it passes through the lungs, where does it go? Into our bloodstream. As it goes about its business of destroying our bodies. Let's use pneumonia. How does it get in? It gets in through our lungs, goes systemic by getting into our bloodstream. Now, once it does that, it's looking for an environment that is hospitable to it so that it can live, it can prosper, and it can move. It can move into parts of the body where we want it to or we don't want it to, but where it wants to go. Now, that's part one of this explanation. Part two of this explanation is a swimming pool. For those of you that live up north, where I originally came from in Pittsburgh, that have a swimming pool, whether it's above ground, in ground, whatever, and come spring, which typically in Pittsburgh is like June, and you go to uncover that pool, which has been covered all winter to keep the junk from flying into it, and you look and you see that the water turned green. Or any of you that have a pool in the South, any place, you know that when the water becomes too, acidic, you start to see green patches show up. Mold starts to show up in corners of the pool. And eventually it can take over the entire water, and the water can turn green. Well, guess what? As God created our bodies, did he mimic a swimming pool? Sorta, kinda. But our systemic pH, all those fluid levels in our body need to operate in an environment that is neutral. Now, for those of you that are familiar with swimming pools, you know, you go buy dipsticks at the swimming pool store and you check the pH of the water. And if it's, again, as you know, what's amazing is when you look at scripture and you look at Bible, what's that magic number? What's that magic number that shows up everywhere throughout scripture? 7. 7 years, 7 days. Over and over again, it's used. Both the Old and New Testament, 7. Well, guess what? As God created our bodies, what's pH neutral? They assigned the number 7 as pH neutral. So if we determine that our body is too acidic, the bacteria has an environment it loves, and it can move, and it can propagate, and it can spread, and it can do the harm it wants to do to us. But if the body's alkaline on the other side of the spectrum, higher than 7, all of a sudden that bacteria entered a chaotic medium where it can't move as rapidly, where it's slowed down substantially, so that our own God-given immune system can go and attack it. Now, this principle affects everything from COVID to cancer and everything in between. Our bodies operate at a neutral pH, ideally. Why do you think it is when you go in to just have your yearly and they do your blood work and they do a urine screen too? They tell you go down to the restroom and pee in a cup and give it to us, and then you get the report. Did you ever see that there's a pH that shows up in that blood work? And if you're like most Americans, it's going to come in with a 6 or a 5 or even a 4. I don't think it goes down to 4, but a 6 or a 5, because they don't break it down into tenths. But both of those are very acidic medians. And in those acidic medians, bad things can happen. Scientists at the University of Exeter have developed a novel method which allows users to measure the pH of individual bacteria before, during, and after treatment with antibiotics. You can do the same thing. We have human pH tape that's available at our office, 678-228-8900. How do you measure? What are you going to measure? The best measurement is your first morning urine. Not if you wake up during the night. No, first morning urine. That is the closest approximation we can have to whole systemic pH, because the kidneys work overnight to eliminate any excess acid. The research published in journal MBio lays the foundation for understanding the special properties of bacteria that survive being treated with antibiotics, so that new ways of targeting them can be developed. The Exeter University research team found that even before antibiotic treatment, common infection causing E. coli cells that can survive treatment have a more acidic intracellular pH compared to clonal cells that are eliminated by the antibiotic treatment. So in this case, E. coli, a bacteria, lives in its own little world that's very acidic. These surviving cells are called persisters because they're responsible for persistent bacterial infections and contribute to antibiotic resistance. Antibiotic resistance is one of the most pressing public health challenges and threatens the ability to effectively fight infectious disease, with around, you ready, 10 million people predicted to die annually of infections by 2050. The University of Exeter research team has discovered the mechanisms that permit persisters to have an acidic pH. By measuring the genetic properties of these cells, they found that 2 cellular processes, namely tryptophan metabolism and carboxylic acid catabolism, are responsible for low pH measured in persister bacteria. That just means there's a difference in that bacteria's ability to produce energy. We've talked about that so many times on this show and others about mitochondrial functioning, that there will be a metabolic waste involved at the end of the burning of glucose. I use the analogy again of a burning barrel. If you've ever had one of those and you were able to burn your newspapers, and you went out back and burned the newspapers, and all of that ash settled to the bottom. And if you measured the pH of that ash, that black burnt ash, it's extremely acidic. And if it starts to build up, it interferes with the oxygen content coming into that burning barrel, and the fire goes out. Much like with us. Dr. Stefano Pagliara, biophysicist in the Living Systems Institute, led this research at the University of Exeter. He said, quote, "Our findings indicate that the manipulation of the intracellular pH represents a bacterial strategy for surviving antibiotic treatment. Our new data suggests a strategy for developing antibiotics that interfere with key cellular components of persisters and decrease their acidity." So we're looking for a new way for the pharmaceutical industry to develop antibiotics that aren't really antibiotics. They're not antibacterials. They're actually something that are going to raise the systemic pH. The team is now working on expanding this research to find out whether cell acidity is key for antibiotic resistance. Yes, it is. And other critical bacterial pathogens such as Pseudomonas and Burkhardia, and identify drug molecules that could alter the pH of persister cells before antibiotic treatment, such as buffered forms of vitamin C. Why do you think we call it buffered? Because it raises systemic pH by just the consumption of calcium ascorbate. Such a simple process. Tomorrow on the show, we're going to talk about C is for vitamin C. Okay, and we're going to talk about the differences between ascorbic acid and buffered C. But for today, the lesson is check your pH, check your pH, check your pH. It's extremely critical to check your pH every day to see what's going to make it go acidic. Stress, diet, stress, diet, stress, diet, stress, diet. How many times do I have to go into that? The acidic waste that goes over a highly inefficient system. Those that are obese, highly acidic. Those that are diabetic, highly acidic. Those that are fighting cancer, highly acidic. There are specific ways to alkalize your body. Drinking alkaline water is one of those. Adding baking soda to your water is one of those. Sucking on a lemon is another one of those. It's a whole myriad of ways to do it. Give us a call, set up your time. We'll discuss that with you on a one-on-one, 678-228-8900, or visit us on the website at thenutritionshop.net. Hopefully this helps. Share it with others, would you? God bless you, and we'll see you back here soon. Take care.